Good afternoon, students. Now we are going to start second unit. This is continuity. This is your syllabus: continuous functions, properties of continuous functions, uniform continuity, limits of functions. There are only 4 topics are there, right? Each topic depends on definition only. This is very important. Now, see. Now, unit 2 continuity, right? Now, what is our syllabus? Continuous functions, properties of continuous functions, uniform continuity, limits of functions. Now, here definition is very important. First of all, I am going to define the constant function. What is constant function here? A function is said to be a constant function if the range is a singleton set. Now, see here, f of x is equal to 2. I have given for all x belongs to 1 comma 3. Now, if you substitute f of 1, what you will get? 2. F of 3, you will get 2 only. F of 1.5, 2 only. F of 2, 2 only. F of 2.5, 2 only. Because here x belongs to what? X belongs to closed interval 1 comma 3 means x lies in between 1 and 3. Collection of all real numbers which are in between 1 and 3. Real numbers means 1.1, 1.2 and so on up to 2.9, 2.99 and so on, including 1 and 3, right? Now, now f of x is equal to 2 means here if you substitute x is equal to 1, you are getting 2 only because there is no x on the right hand side of the function. Right? X, if you substitute x is equal to 1.5, also you are getting the same thing. X is equal to 2, also you are getting the same thing. X is equal to 3, also you are getting the same value. Right? That means for all x, the function value is equal to 2. Therefore, that means the constant function. It is said to be a constant function. What is the definition? A function from R to R defined by f of x is equal to k, where k belongs to R for all x is called a constant function. Now, what is the range of the constant function? A singleton set which contains 2. That means for each x value, what is the image? 2 only. That means the collection of images is 2 only. It is a singleton set. Next, identity function. A function f is from R to R defined by f of x is equal to x is called the identity function. The range of f is equal to R. In that case, domain is equal to codomain. Now see, here A is a set, B is a set. Now 1, 2, 3 I am giving you. Here also 1, 2, 3, F. Now 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3. That means f of x is equal to x. If you substitute f of 1, x is equal to 1, then what you will get? 1 only. If x is equal to 2, f of 2 is equal to 2. X is equal to 3, f of 3 is equal to 3. Right? Now this is called domain. This is called codomain. Right? Now this is also called collection of images, is called a range set. Okay, now if f of x is equal to x, for all x belongs to the domain means the first set. Now then that function is said to be a identity function. Then domain is equal to codomain, range is equal to codomain. Then range of f is equal to, what do you mean by range of f? Collection of images. Collection of images is equal to nothing but domain only. See, what are the images? This is the image of 1 under the mapping f. This is the image of f under the image of 2 under the mapping f. This is image of 3 under the mapping f. Right? Now if you collect all the images, this is nothing but domain only. Range of f is equal to domain of f if it is an identity function. Next one, absolute function or modulus function. A function f from R to R defined by f of x is equal to x. If x greater than or equal to 0, f of x is equal to minus x. Right? And if f of x is equal to minus x if x less than 0. Now is called a modulus function or mod function. It is denoted by f of x is equal to mod x. See this symbol notation. The range of f is equal to 0 to infinity. Right? Now you can take an example. See, now a simple example I am taking f. Here 1, 2, 3, 0, minus 4, minus 5. Right? See, for example, I am taking only 6 elements are there. Now see here, f of x is equal to mod x is given. Now you have to find the image of 1. F of 1 is equal to mod 1. Mod 1 is 1, right? Now image of 1 is 1. Now next element is 2. F of 2 is equal to mod 2, 2. F of 3 is equal to mod 3 is equal to 3. 2 is mapped to 2, 3 is mapped to 3, and 0 is also mapped to 0. Next minus 4 is there now here. F of minus 4 I am finding. See, f of x is defined as mod x. That means mod of minus 4. Modulus of minus 4 is minus of minus 4, which is 4. Right? Minus 4 is mapped to 4. Similarly, f of minus 5 is equal to mod of minus 5, which is nothing but minus of minus 5, that is 5. Because here the x value is less than 0. In that case, how to write mod x? Mod x is nothing but minus x if x is less than 0. Here x is minus 5, which is less than 0. Mod minus 5 is equal to, as per definition, minus of x value is minus 5, which is nothing but 5. Now minus 5 is mapped to 5. Now what are the images here? See, the images are 0, 1, 2, 3, 4, 5 only. All are positive numbers, no? Therefore, the images are, the range set is always equal to 0 to infinity. That means it is a positive set, no negative values. If the domain contains negative values, then its range is always equal to a positive value, right? See, therefore range of a mod function is nothing but 0 to infinity. This is the range of a function, whatever it may be the domain. For any domain, range of f is equal to 0 to infinity in the case of mod function or absolute function. Next, a function f is said to be a real valued function if the domain of f is subset of R. Now, see here, what is the definition of a real valued function? A function f is said to be a real valued function if the domain of f is a subset of R. See here, now what is the domain here? 1, 2, 3. Whether this 1, 2, 3 is subset of real numbers or not? Yes. 1 is a real number, 2 is a real number, 3 is a real number. Therefore, this domain set is subset of R. Therefore, this function f is said to be a real valued function. Right? Now, f of x means, now here another point is there. Now we are writing f of 1. What do you mean by f of 1? This is nothing but image of 1 under the mapping f, right? That is nothing but 1. Now here this is nothing but what? Image of 2 under the mapping f. It is denoted by f of 2. What is f of 3 here? This is nothing but image of 3 under the mapping f. Therefore f of 3. Similarly, tell me what about f of t? This is nothing but image of t under the mapping f. All these images are in codomain only, remember, right? Similarly, f of x means what? Image of x under the mapping f. Therefore, this f of x is always belongs to codomain only, where x belongs to domain. F of x is always image of x under the mapping f. Now, see, f of x means the value of the function at x, or you can say image of the function. Next, continuity of a function, important definition, very very important, right? Based on this only you will get theorems. Now if you know this theorem, then only you will get the theorems. Now let f be a real valued function. The function f is continuous at a point, at a single point I am timing, in the domain of f if every sequence xn in the domain converges to x naught, right? Whatever it may be the sequence in the domain only, domain means first set, that converges to x naught, right? You know what is the definition of a convergence. A sequence Sn is said to be convergence if mod of Sn minus L less than epsilon, or you can say limit Sn is equal to L as n tends to infinity. If Sn is set, then if you write like this, Sn limit Sn n tends to infinity is equal to n means the sequence Sn converges to L. Another definition is mod of Sn minus L less than epsilon, then Sn is said to be convergent to L. Similarly, if limit of xn is equal to x naught means what? The sequence xn converges to x naught. That means xn minus x naught is less than epsilon by definition of convergence. Here the sequence we are denoting it by Sn. Here we are that sequence is denoted by xn only. That is the difference. Now xn in the domain convergence to x naught, that is limit of f of xn is equal to f of x naught. X naught tends to xn tends to x naught. Similarly, limit f of xn tends to f of x naught. If f is continuous at each point of the domain, so see, of course, here example, how many points are there? 1 2 3. That given function is continuous at 1, continuous at 2, continuous at 3. That means at each point of the domain the function is continuous. That means the function is continuous on the domain, entire domain, and that means sorry, f is continuous at each point of a set S, that is subset of domain, then f is said to be continuous on the entire set. Entire set means that codomain set. If the function is said to be continuous if it is continuous on entire domain, right? Entire domains at each point of the domain, if the function is continuous, then the function is said to be continuous. If it is continuous at a single point only, then we have to mention it very clearly. The function is continuous at x is equal to x naught. Right? That means the function is continuous at a single point of the domain, but it is not continuous on entire domain. If it is continuous at each point of the domain, then we can say that f is continuous, means the entire domain. Now, there is an important theorem. First theorem, let f be a real valued function whose domain is a subset of R, then f is continuous at x naught belongs to domain of f if and only if for each epsilon greater than 0 there exists delta greater than 0 such that x belongs to domain of f and mod of x minus x naught less than delta, imply f modulus of f of x minus f of x naught less than epsilon. This is a theorem statement and this entire thing is a statement. Okay. Now see, if and only if is there, no, that means we have to prove one implies another. One implies another means if f is continuous we have to prove this condition. If this condition is satisfied we have to prove that f is continuous, vice versa. Okay. Now first of all we are writing the given data. What is f? F is a real valued function. Domain of f is subset of R. Reason is here the f is real valued. Real valued means by the definition of f the domain is subset of R. See, right? Now for each epsilon greater than 0 there exists delta greater than 0 such that x belongs to domain of f mod of x minus x naught less than delta, imply f of x minus f of x naught less than epsilon. This is we are taking, this is our assumption, right? This is our assumption. With the help of our assumption we have to prove that f is continuous at x naught. That is, let us suppose that I wrote the entire statement. We have to prove that f is continuous at x naught, right? Now when do you say that a function f is continuous x naught? We have to go through the definition. What is the definition? If there is a sequence in the domain, that sequence converges to x naught. or else limit f of xn is equal to f of x naught, we can say that f is continuous at x is equal to x naught. We have to get this result, or we have to show that the sequence xn converges to x naught. Either this condition or this condition we have to prove. See, now consider a sequence. To prove that thing, we have to take a sequence from the domain. No? That's why you're taking the sequence from the domain f, such that limit xn is equal to x naught. There is a sequence which is convergent to x naught. Then we have to prove that limit of f of xn is equal to f of x naught. If we get this condition, we can say that f is continuous at x is equal to x naught with the help of this entire data. Now, to prove that f is continuous, it is enough to prove that limit of f of xn is equal to f of x naught as per our definition. Okay. Now, see. For each epsilon greater than 0, there exists delta greater than 0 such that x belongs to domain of f and mod of x minus x naught less than delta and f of x minus f of x naught is less than delta. We know the definition, no? From the definition as it is I am writing. Since limit xn is equal to x naught, there exists capital N such that for n small n greater than n, mod of xn minus x naught less than delta. Right, we are using the convergence definition, and n for n greater than capital N, mod of f of xn minus f of x naught less than epsilon. Now, what does it mean if I get this condition? Say mod of Sn minus L less than epsilon means limit as n tends to infinity, Sn is equal to L, no? Right, from unit 1. Now this can be written as limit as n tends to infinity, f of xn is equal to what I have to write? F of x naught. I got the result. Therefore, I can say that f is continuous at x is equal to x naught, which belongs to the domain of f. Right? Now, and the next one is converse of this theorem. We prove this converse by contradiction way. Contradiction way means we have to assume that f is continuous at x is equal to x naught. We have to prove this condition, right? Now, to prove this condition, we are assuming that this is not less than epsilon. That is, it is greater than epsilon. Assume that equation 1 is not true or fails or does not holds good. Right? That means for each condition, this condition, mod of f of x minus f of x naught is not less than epsilon. Right? Fails for delta greater than 0. Now, we are writing as it is the definition, right? X naught minus xn less than 1 by n as it is condition for fails for each 1 by n belongs to n. For each n, there exists xn in the domain such that mod of xn minus x naught less than 1 by n, where which is less than delta, no? And yet mod of f of xn minus f of x naught is greater than or equal to epsilon. Thus, limit xn is equal to x naught. Limit of f of xn is not equal to f of x naught, because this condition does not holds good, no? If it is less than only, we will get f of x naught. Since mod f of xn minus f of xn is greater than or equal to epsilon for all n, f cannot be continuous at x naught. Thus, on a contrary, that means this is a contradiction to our assumption or hypothesis. Therefore, our assumption is wrong. Our assumption is wrong means its negation is true. Therefore, for each epsilon greater than 0, there exists delta greater than 0 such that x belongs to domain of f and mod of x minus x naught less than delta implies mod of f of x minus f of x naught is always less than epsilon. Important theorem. Please go through this theorem carefully. Tomorrow we'll discuss about the problems on continuous functions. Right?